Hello, Professor.
Mm-hmm.
How are you there?
It's starting to rain, I think.
My name is Rayhan. You can just call me Ray, and I will moderate this meeting.
Mm-hmm.
I hope you can hear me fine there.
Absolutely. Perfectly
Thank you
fine.
so much. Yeah. So we will start like, or maybe we can just start strictly at 4 in here.
Anytime you want, I'm ready.
We still have 3 minutes more.
Sure.
So, Professor, I just want you to know that we have more than 200 people assigning to join this meeting.
Oh, that's
And
excellent.
yeah, most of them is high school students, college students.
Mm-hmm.
Some of them also like employees, and then some of them also are the junior high school. And then most of them, of course, coming from Indonesia, but we also have guests coming from like India, the country, of course, and from Bangladesh, Philippines, Sri Lanka, and also as well as Brunei Darussalam. So we kind of welcoming them not only from Indonesia but also from Southeast Asia. And so we can just okay. How about we start, Irshad?
30 minutes.
Still okay. So how's in Bangalore, Professor? Still summer there?
It's no, it's monsoon now.
Monsoon now. Okay.
It's soon, so quite cold.
Quite cold. Okay.
July is our coldest month. It gets down to maybe 13.
Oh, really?
12, 13.
Yeah.
But every day rain.
Oh,
really? We still got rain sometimes here, and it should be summer here, but the weather is not very good. Sometimes we got rain. Sometimes we often to get a cloudy. So here the amateur astronomy here finds so it's not too good for the sky for this year.
Yes. We also here, Bangalore is so bright. You can hardly see 4th or 5th magnitude stars.
Oh yeah, it's a big city, right? Bangalore?
Big city. 10 million people.
10 million? Just like Jakarta here. Jakarta is also like 10 or 11 million here.
Oh, that's all, is it? Okay. I thought Jakarta was bigger.
Yeah, it's a capital city, so lots of people here, lots of pollution.
I heard we have similar traffic. Very bad.
Of course, and also Jakarta once mentioned as the worst traffic in the world. Sadly.
Yes. And you have lots of what we call autos. I think you call tuk-tuks.
Yeah, but most of them is a motorcycle actually. So,
is it? Okay.
Yeah, it's motorcycle. Tuk-tuk can be much, but right now it's not as much as the motorcycle because most of them is owned by personals, but another one is owned by transportation services, but using a motorcycle. So because it's easier to get around to use a motorcycle here.
Sure. I don't trust motorcycles.
Yeah. Okay, it's 4 p.m. here now. Maybe we can start, Irshad.
Hello everyone from anywhere you can from. Today we will going to live in YouTube, and also for the some reason, please do not recording alone for yourself, because some right will be it's illegal for you. And also we will welcome to weekly routine meeting of Amateur Astronomy Association of Jakarta. And today we will be with Professor Jayant Murthy, will speaking in space astronomy, and the time is yours, Muhammad Raihan and Professor Jayant Murthy. Yes.
Okay.
Okay.
Shall I?
Thank you, Rishad. Hello, everybody. Welcome to Astronomy Online Meeting and Jakarta Amateur Astronomy Association. Please introduce myself. My name is Raihan, and I will be the moderator for this meeting. Still in the pandemic situation, we hope everybody is safe and sound. And now we reach a 10 online meeting today. And this meeting is very special because this time we collaborate with the International Astronomical Union in the program of Meet the IAU Astronomer. And already with us is a very special guest, an IAU Astronomer, on Bangalore, India. And also, Professor, we are so great to have you here, and thank you so much for your time. Professor Murthy will sharing his knowledge and experience with us about space astronomy. What is space astronomy and how it become a very important topic in this modern era of astronomy. We'll hear later. And so to make it short, we welcome Professor Jayant Murthy to give an introduction and then continue with the subject. Please, Professor.
Okay, thank you. It's my pleasure to be talking to all of you. What I will do is I think what we had planned is I'll give a short talk, maybe about half an hour, and then we'll open it up for questions. That's, I think, what we had said.
Yep, great, that way.
Okay, great. So I actually have a much longer presentation, so I will not show you every slide. Instead, I'll skip through. I can certainly give you the entire presentation. I'll give you a PDF, and I'm happy to have you share it, but I'll skip through. Before I start, let me just tell you a little bit about myself and about astronomy in general. So this is arranged in collaboration with the International Astronomical Union, and that is actually the main group for professional astronomers. We have national groups, and this is our international group, where about 5,000 astronomers from around the world are all members of the International Astronomical Union. It's been around now, I think, for 75 years. We just had our 75th anniversary recently. I myself am at the Indian Institute of Astrophysics. I did my PhD from Johns Hopkins University long before any of you were born in 1987. And I was 2 years at NASA at the Goddard Space Flight Center. I didn't like it. It's a government bureaucracy, and I didn't like it very much. After 2 years, I went back to Johns Hopkins, and I was there until 1999, when I joined the Indian Institute of Astrophysics. And what I do now is two things. We have I do my own research on what is called the interstellar medium, which is matter between the stars. Almost all hydrogen, of course. Everything in the universe is hydrogen, but also dust and gas that's between the stars. And we also build small satellites or small payloads, small instruments for space use. So what our group is doing now is we're building a small spectrograph for the Chinese space station. And when hopefully that will be launched in 2022 or 2023, and we'll take observations of the sky. So that's a little bit about what I do. The Indian Institute of Astrophysics is the largest astronomy institute in the country, by the way. All right, so what I will talk to you about today is astronomy in space. And so like I said, I'll skip a lot of the slides. Just a very brief introduction. The main people behind this were Tsiolkovsky, who was the first person to really put space astronomy on a physics basis. We all know the stories. We all know stories about people going into space. You, I think, also know about Indra and Garuda and all the ancient mythology. But Tsiolkovsky was the first person to say, okay, these are the equations that govern spaceflight, back in the turn of the 20th century. Goddard was the pioneer of liquid fueled rockets in the 1920s. Wernher von Braun, we know this is him. He is here in the this is him in his office at NASA headquarters in Washington, D.C. But before that, he was in charge of the German space program. Not the German space program, but the German bomb program. So he was in charge of the V2 rockets, which were intended to bomb London into submission. So this is from Tom Lehrer. Once the rockets are up, who cares where they come down? So that was Wernher von Braun. The equivalent on the Russian side was Sergey Korolyov, and he was the main person behind Sputnik, Yuri Gagarin, the first successes of the Russian space mission, of the Soviet space flight. Now, Korolyov himself, no one knew about him when he was actually working, because this was the height of the Cold War. You had the American side, you had the Russian side. And so the Russians were afraid that the Americans would send an assassin squad over to kill, CIA would send an assassin squad over to kill Korolyov. So during the Soviet era, he was always known only as the great designer. It was only after the fall of the Soviet Union that everything was released and people understood the work he had done. So the space era started with Sputnik, and this is Sputnik. It was a football-sized object that just went around the world. That's all it did. It went around the world. It had a radio set on board, and anyone with a ham radio set could hear the beeps that it said. But of course, it's not just beeping. Remember, this was the height of the Cold War. Excuse me. The height of the Cold War, and everyone was afraid of nuclear bombs. So this is a famous, this is called, he's Bert the Turtle, and he's told to duck and cover. Anytime there was a nuclear attack, he was supposed to go into a shell and cover. And so this was the big thing about Sputnik. Because now the Russians showed that they could go all around the world, obviously they could stop halfway, and you could launch something from the Soviet Union and hit any city in the United States. And so this caused the Americans to essentially panic, and they put a lot of money into anything to do with space science, anything to do with rockets. I hope this video comes through, it's a short video. The first American rockets were just not very successful. And so this is the Vanguard 1, and you'll see what happens to it.
There were a number of failures during the United States.
You see, normally rockets are supposed to go up. This decided to go to the center of the Earth instead. And so the first few American missions were all failures, first few American rockets. And so, of course, the newspapers, they called them things like Flopnik and No Good Nick. After Sputnik, No Good Nick, and so on. But then they then went on from that. The first American satellite was Explorer 1, which was launched by Wernher von Braun and his team at Huntsville, Alabama. And by the early 1960s, Kennedy said, it's time to go to the moon. Before the end of the decade, we will send a man to the moon and bring him back. And so, so the Apollo program started. These three people are the Apollo 8 astronauts, which is the first mission to go to the backside of the moon and come back. And then this is the canonical picture from Apollo 8. It's the Earth rising over the moon. And this picture was actually very important for the environmental movement, because when you look at this picture, you see how desolate the moon is. Buzz Aldrin called it the magnificent desolation. So you see, there's nothing there. All we have is the Earth. And when we're ruining the Earth, you know, climate change, pollution, all of this, this is where we live. This is all we have. One blue marble in the sky. And then the next flight, then came Apollo 11. And Apollo 11 is the first mission that I remember. I barely remember Apollo 8, but I watched Apollo 11, 1969. I watched them land on the moon, and you know, a small TV set, really terrible video, but I watched them. I watched them land on the moon. And so maybe in some ways, this was the inspiration for me to go into astronomy. Now, I know many of you have heard about the moon hoax, and I won't say anything about it because there's so much good science in the world. Why should you worry about bad science? But anyone who's interested, go to this website, badastronomy.com, and they'll give you all the information you want to know. The one thing I always hear is, why is the flag waving? And you know, I only remember things I'm interested in. My brain can only hold so much information. And so I only remember things that I'm interested in. And you see here two pictures of the flag. This is Buzz Aldrin. He's in one picture, he's saluting the flag. In another picture, he's got his arms by his side. And you see that the astronaut moves, but the flag doesn't. And the reason for this is because NASA had a spring that would extend the flag out all the way. But things are hard in space. And so when they launched Apollo 11, or when they tried to plant the flag on the moon, that spring broke. And so the flag didn't extend out all the way. Now, when we see flags, normally they look like they're waving. So NASA liked it that way. And on all future missions, they didn't extend the spring so that the flag always looked like it was waving. Okay, so the Apollo mission was a political angle. It was launched because of the Cold War. The Americans wanted to show that they were better than the Russians. And so it was not an astronomy mission. It was not a science mission. It wasn't until the last of the Apollo missions, Apollo 17, that they actually had a scientist on board, Harrison Schmitt, who was a geologist and who brought back lots of rocks. So that was not science. And now we know of space for many other things. Here we have a picture, I show it because it's off the eastern coast of India, but Indonesia must be somewhere around here. And it's always a good thing to know when cyclones are around. So weather satellites, an important use of space, of going into space. Then remote sensing. One of these places is my house. I won't show you which one, but one of these is my house. And remote sensing is very important for, we can tell how much tree cover there is. In India, the tree cover is somewhere around, I think the number is about 15%. So you can tell that from this kind of picture. You can see where we're growing wheat, where we're growing rice, and so on. So remote sensing, very important. Other things, military applications for obvious reasons. Instead of having a plane go overhead, you have a satellite go overhead, and you see what the North Koreans are doing. So military applications very important. Now we all have phones with GPS, so no one knows how to read a map anymore because your phone tells you where you are. So these are all the benefits of going into space, and this is why everyone wants to have space missions, because of all these commercial applications. But that's not what I do. I do science. And so the question is, well, firstly, why do we do science? And I think this is an important question. And you know, I won't go into all the details because I don't have time. But really, I think we go into science because we're human. We have a need to learn about the universe around us. We want to understand what the universe is like. And so I think that it's important that we do curiosity-driven research. We do science just because we want to know more. This is something that maybe we can discuss, or maybe you can think about, but I do think that we need to do it. It's a hard thing to explain to politicians because politicians don't have that long vision in general. So at least our politicians don't have that long vision. So but this is why we do it. We do it because science is important. Now, why do we go into space? See, there's all sorts of reasons to not go into space. Space is expensive. This is the fuse payload inside a Delta II rocket that's gone up. The cost of the rocket is $70 million. The fuse instrument was another 100 million. So going into space is expensive. And once you go into space, there's no room for mistakes. And I have all sorts of examples of spacecraft that failed because of errors. I'll only tell you one, which is the Terriers mission. It was done by my friend Supriya Chakrabarty at the University of Boston. They were supposed to point at the solar panels are obviously supposed to point at the sun. That's how you get power. But instead of a +1, they put a -1. So instead of the solar panels pointing towards the sun, the solar panels pointed away from the sun. And so the spacecraft the satellite ran out of power within a few minutes, and the whole experiment failed. So space is difficult. So why do we want to go into space? So one reason is because the sky is bright. Because the sky is opaque. So in this picture, you can see that we can see in the visible. We can see all the way from the blue to the red. We have a telescope, we look up, the sky that we see, it's what we see with our eyes. We can also see in the radio waves come down to the earth, but we can't see in the ultraviolet because we have the ozone layer here. And so you have to go above the ozone layer if you want to see in the ultraviolet. We can't see in many of these bands because of water. So you have to go up to high mountains or again to space to see this. So one reason to go into space is because there's lots of the electromagnetic spectrum that we cannot see. Now, that wouldn't matter if we saw the same thing at every wavelength. So if the ultraviolet sky was the same as the optical sky, it just wouldn't matter. We could just say we look up in the optical and that's what we see. but that's not true. Now, I don't know if you know about the electromagnetic spectrum yet, but all of everything from gamma rays to radio is part of what we call the electromagnetic spectrum, of which the visible light is the part in I guess sort of the middle. Now, the importance of this is that at the very at the very shortest wavelengths, gamma rays, you have the highest energy. At the very longest wavelengths in the radio, you have the lowest energy. Now, energy is really nothing but temperature. The faster things move, the hotter they are. So when we look in gamma rays, we see the hottest parts of the universe. When we look in radio waves, we see the coldest parts of the universe. So we see all the way from black holes, remnants on one side, to the 3-degree microwave background on the other. So when you look at different wavelengths, what you're really looking at are different temperatures in the sky. You're looking at the very hot in the shortest wavelengths, very coolest in the longest wavelengths. So this is the central disk of our Milky Way in different wavelengths. So here we have the radio, and what you're seeing there is largely cold molecular gas. The visible is here, and what you see here is stars, the stars that we normally see. And you see dust lanes, this black stuff in here, that's interstellar dust that you're seeing blocking the light of more distant stars. It's, you see that over here, for instance, is the Coalsack Nebula, and that's a patch of dust that's blocking the Milky Way. And you see that same patch in the infrared because the dust that absorbs the radiation in the UV re-radiates it in the infrared. And so by looking at different wavelengths, you get different information about the same objects. And when you look in the gamma ray and the X-ray, what you see are individual bright spots, which are things like largely black hole candidates, supernova remnants, things like that. So the hottest parts of the universe. Other reason to go into space, because the sky is bright. You know it if you go outside, you might see 100 stars. I know everyone says 6,000 stars, but you actually go out, you can count the number of stars that you see. I'm sure Jakarta is no different from Bangalore in that way. 100 stars, 10 stars, 10 stars. But no matter where you are on the Earth, you will, the sky is bright. And so even for these telescopes in Chile, where they're far from civilization and the sky is bright, I mean the sky is dark, it's still bright for astronomical purposes. And so here's a picture of Orion, the only constellation I can recognize. I should apologize for not being an astronomer. I'm really a physicist who does astronomy on the side. So here's Orion, and you see Orion from the space station, and here's the Earth's atmosphere. So you can see how muddy the Earth's atmosphere is. Orion is clear, his head is clear, you can see everything, but his feet are in the mud. So, so that's two reasons to go into space. And then the final reason is because of atmospheric twinkling. You know that stars twinkle. The reason that they twinkle is because you're looking at it through the entire atmosphere. And the atmosphere has thousands of these little microcells. So you have little turbulence where the air is moving around. And as it moves around, the density changes. And because the density changes, the index of refraction changes, density and temperature. The index of refraction changes. And so the position of your star changes by about an arc second. So when you look up at a star, you will see it twinkle, both because the brightness changes a little and because the position is changing a little. Planets don't twinkle because they're large enough that they don't twinkle. And so here, when we look at, here's a galaxy, here's the square in the middle. You see the square here. And this is that same region seen with the space telescope. And so you can see how much more clear it is. It's like the difference, you know, I wear glasses, so it's like the difference between glasses on and glasses off. Glasses off, I can't recognize anyone. Glasses on, you know, I can actually see things. So here you see that there's this star formation, these bright stars around this central dusty glob. Whereas from the ground, all you see is just smear. So we go to space because we see new wavelength regions, because of the freedom from the city lights, and because there's no twinkling. So let me go on. I'll just tell you a little bit about I'll just give you a little bit of a glimpse into the science that has come from space. And much of the science has come from NASA. So you can go to this website, science.hq.nasa.gov, and they have a list of all of their missions. You can click on any of their missions, and it will give you information about that mission, usually at a level that's understandable. They have different levels, anyone from kindergarten to 12th and beyond. So you will usually find something that's at your appropriate level. And so just a few of the highlights. This is from the Kobe mission. And what you see here is radiation from the universe. And this is called a black body curve. And what a black body curve is, I won't go into it in detail, but a black body tells you the temperature of whatever you're looking at. Almost everything you look at is a black body, modified a little bit by its own properties, but basically a black body. And so this is the spectrum of the universe. It tells you that the universe is at 2.725 degrees Kelvin. The only way this could happen is if you have a Big Bang. So this is definitive proof that the universe started with a Big Bang. No other way. Any other way, you have to really try to complicate things and do all sorts of stuff. But that shows that the universe started with a Big Bang. This is one of the more famous pictures from the Hubble Space Telescope. And this is the Eagle Nebula. The Eagle Nebula. Some people call it the fingers of God. And what you see here is dust and gas. So these huge pillars are just dust and gas. And you have these red stars inside these pillars. And those are actually not red stars. Those are actually hot blue stars. The reason they look red is because we're looking at it through so much dust. So, you know, when there's a lot of pollution in the air, the sun looks much redder. In a similar way, slightly different process, but in a similar way, when you're looking at the stars through the cloud, the star is very much reddened. So these are young stars. These are stars that had only just been born, maybe a few million years ago. So this is stellar nurseries, where new stars are born. Okay, and another picture from the Space Telescope. What this is a long slit. Here's a spectrograph. You can see the long slit here. And they laid it across the center of this galaxy, M84, nearby galaxy. And what they saw was whether the light from stars in that galaxy was red shifted or blue shifted. So when you're far from the center, it's nothing. It's basically the stars are all just moving around. As you get closer and closer to the center, now suddenly the stars are very much blue shifted. What does that mean? The stars are coming towards us very fast. Like an ambulance, the sound increases as it comes towards you. Here, the light is shifted towards shorter wavelengths. Here, the light is red shifted. The stars are going away from us. Here, they're coming towards us. You can tell how fast by how big this is. Here, they're going away from us. So as you cross the center, the stars are coming towards us, and then they're going away from us. And so the only way that can happen is if you have a black hole right there. And how do you know it's a black hole? You can measure how much the mass is there by Kepler's laws. We use Kepler's laws in our solar system, so we can weigh the sun. In the same way, you can weigh the black hole here by the amount of the deviation. The stars are all going around that black hole, and by Kepler's law, you can measure the mass of the black hole. It happens over this very small range, and so that tells you that there has to be so much mass in such a small volume. Only way that can happen is if you have a black hole. So I know you can't see a black hole, But here, you really do see the black hole. Black hole is in the center. And I'll just show you what it looks like in our own galaxy. Our black hole, the central black hole is where this cross is. And so these are pictures, these are measurements of stars as they orbit around the black hole. And you see this star here, you see how it suddenly whips around. So this is like a comet. A comet, when it comes like Neowise, when it came around the sun, very slow when it's far away, and then it comes near the sun, speeds up, zips around the sun, and then goes back far. And that's what the star is doing. See? Zips around that black hole. Okay, let me just show you a couple more slides, and then we can go on to the questions. This is the LISA mission, which has not yet launched. And the reason I'm showing it is because I'm sure you've all heard of LIGO, which measured the black holes colliding. And so LIGO is on the ground. And the way it works is that you measure interferometry, and you very carefully measure the distance between these sets of mirrors. And when that changes because a gravitational wave goes by, you measure that difference. But on the ground, we have all sorts of noise. Firstly, the size of these is only a few kilometers, 4 kilometers. Sounds like a lot, but it's not when you're trying to measure gravitational waves. If you go out to space, then you can have mirrors separated by thousands of kilometers. So you can measure gravitational waves of a much different frequency. The second thing is, out in space, you don't have North Korean nuclear tests or earthquakes or any traffic going by. It can be much quieter. So again, you can be much more sensitive. So all of the telescopes that we're used to, they're almost all electromagnetic radiation. We measure light in one way or another. This LISA is a completely new branch of astronomy. It's gravitational wave astronomy. And then just to show you that there is good planetary science, here is a couple of slides from the global surveyor. And you see this deposit here, this bright region. That's water on Mars that's there now. This is August 1999 to September 2005. And so here there was no ice patch. Here there is an ice patch. And so ice, it not only existed in Mars on the past, you know it exists on the Mars in the past, because if you look at the walls of this canyon, you can see these erosion channels. But it also exists on Mars now. Okay, and then here is Kepler. And what Kepler does is, you all have heard of all of the exoplanets that we found now. So now there's several thousands of them, and almost all of them have been found by Kepler. And just to put this in perspective, when I was a student, we only knew of one solar system, ours, and everything was nice. You had all the rocky planets near the sun. You had the Jovian planets, the gas giants far from the sun, where it's cold, rocky planets near where it's hot. But Kepler now gave you a huge variety of planets. This is just all the systems in Kepler. A whole variety of planets, all the way from hot Jupiters, Jupiter-sized planets that are very near their star. They're going around their sun in only 4 days. Even Mercury's orbit is 56 days. But these planets are going around in 4 days. And so hot Jupiters with temperatures of 1,000 degrees. If the planet's temperature is 1,000 degrees, how can it hang on to its atmosphere? So all these planets that are solar systems that are completely different from ours. Planets with 5 stars. You wouldn't think that would be stable. You would think that somewhere in their collisions, the planets would be thrown out. And yet you have this, planets with 5 stars. And so let me end by just flashing this slide on the virtual observatory. Now, astronomy all along has been very much a personal activity. You take your photographs, you go to the telescope, you take your pictures of the sky, you put those pictures of the drawer in your drawer. If your friend asks you, it depends on how you feel. You may or may not let them look at it, but they belong to you. Now, once space astronomy came along, now it's too expensive to go out and to launch a new telescope for every observer. Plus, the other issue is that really the taxpayer has paid for the mission. It's not paid for from my private fortune. And so the data should really belong to the taxpayer. So this is what the current paradigm in astronomy is, and it's spreading throughout science, in fact, that really data, whatever it is, protein research, genetic research, astronomy research, ground-based telescopes, whatever it is, the data should be open to the public. That in practice, this means often fellow scientists, but it doesn't have to be. It can be to the public. Now, we all have, everyone who's at this talk has reasonable internet access. So you can actually download data. You must have a reasonably fast computer. You can't see my computer, but it's a little yoga laptop. So I do most of my research, most of my calculations on this little computer. And so really, this has opened up the sky to anyone. You can take data, you can do nice things with it. You can take space telescope images and reprocess them to make them look really nice, to get pictures that show what you want. And if you're interested, you can do real science projects. And certainly we can discuss some of them later if you would like. So let me end here, I think, and have the chat session. If that's okay, Ray?
Yep. Continue, no problem.
Yeah, so I'll stop here.
Yeah, you can continue.
No, I'll stop here. I'll stop and.
Okay. Thank you very much for your talk, Professor. So everyone, we already heard about the presentation from the Professor Jayant Murthy about this space astronomy. It is very interesting topic because we do now know about the limitation about the research, astronomy research based on the ground. So because of the limitations, we do have to go to outer space to get rid of the limitation and can get more exposure for the research itself, not only for the radio or visual. We also have to know about universe with using the window of like UV and then infrared, X-ray and gamma ray and other things. So now we can discuss about this topic more. The participants are allowed to give the question if there is one. If you want to have questions to Professor, you can just use hands up, raise your hand, and then we can just allow you to give the questions. While
anything in astronomy is fine. It doesn't have to be only space astronomy. Everything in this is in space. So anything is fine.
Yeah, we actually have some of the question from our follower in Instagram asking about the IAU itself, because we know IAU is a international organization for astronomy. Yeah, while we wait for the people to ask, the first question maybe for you, Professor, is about maybe Irshad, you can just show up the question from our follower in Instagram.
Raihan,
Mm-hmm.
Mas Yudi
Yeah,
mau
the
nanya.
first. Oh, okay, okay. First question from Mr. Yudiatro. We please you to
Okay.
get the
Can be
question.
heard?
Okay.
Okay.
Yeah, we hear you fine.
Okay. Thank you. Thank you for the moderator and Professor Jayant. My name is Yudi. Currently I'm a physics lecturer in Universitas Ahmad Dahlan and also part of HAAJ, the organizer of this webinar. So I would like to ask, based on your presentations, that you got inspired by the moon landing, and also you mentioned about space is expensive. I mean, like the space astronomy is expensive. So in the past, that the achievement of the people exploring the space was driven by the political that you said, or by the competitions. How do you
Mm-hmm.
see in the future the achievement of human to explore the space? What kind of the driving force that can accelerate the achievement of the human to explore the space, and also the expensiveness of the space is probably the main obstacle of the student in the developing country to get involved in. So how do you see this kind of the problem about the cost of the space astronomy, that probably you have the solutions for the student in developing country, or also the scientists in the developing country, to get involved in the space astronomy, so more people got inspired like you. Thank you.
So let me answer that in two parts. The first part is that the amount of money that is needed for space exploration, or really science in general, is not very much. In India now, we spend about 0.7% of our GDP on science. And that includes not just basic science like the science I do, but also the defense-related science, missiles and so on. So it's not very much money. In China, they're spending, I think, about 4% of their GDP on science. In the US, it's about similar, 3, 4, 5%. And so this amount of money that that is really needed is not that much, even for developing countries like ourselves. And I think that it is my opinion that the money you put in science always comes back, because what we do is we educate people. We teach people how to think. As educators, we teach people how to think. And you find that where does Silicon Valley? Silicon Valley is near Stanford. There's a whole group complex around MIT. In Bangalore, Bangalore is known as the Science City of India, and it's known as the Science City because of the Indian Institute of Science, which is here. So science has this effect. If you put money into science, that money will come back into society, and it will help everyone. Because of this very fact that you're training people. So that's one aspect. I don't think it's that expensive. Now, on an individual level, of course, we're bound by our governments and whatever. So we don't have that choice to spend lots of money.
Yeah.
But what we do have now, and this is what I'm trying to convey with this slide here on the virtual observatory, that now there is so much out there that if you are willing to if you're willing to put in the effort, it's not easy because you do have to do a lot of even to get started, you have to do a lot of research. But if people are willing to do it, then there's a lot of work that can be done even now, even if you have nothing but a computer. I know some people at our local planetarium, they measured the sizes of all the craters on the moon. And so by doing that, you can get an estimate of how many meteors hit the moon. There are things that can be done. So on a national level, I don't think it's much money, and I wish our politicians would put in much more. On a personal level, we really don't need that much.
Yeah, thank you very much for your answer, Professor. It is.
Oh, itu belum tuh. Itu tapi berpotensi dapat tantangan kan?
Hello?
Tapi
yeah.
Okay. we not proceed to the next question first. So it is a big problem in the developed country like in developing country like Indonesia, as well as maybe in India, to have a problem with fund. But it's not always the same idea between the government who has fund with the needs of the scientist and astronomer in this case. So we hope that it's enough for the question, Yudiato. And also another one, we welcome to Widamut to give a question, next question for Professor. Please let Widamut to.
Okay, thank you very much. That was really good, I think. And I have watched Professor Jayant in TED Talk in 2013, so it is an honor to be asking him in this presentation. So we know that last year we managed to take picture of black holes, but it is not in our galaxy. It is in Sagittarius A star. And so is there any chance we can take a picture of black hole in our galaxy? If there is anything that need to be prepared for to take a picture in our black hole in our galaxy. I think that's enough.
To take a picture in our galaxy?
Yes, black hole, our black hole.
To take a picture of our black hole. Yes, yes.
Because the center of a galaxy is
yes.
black hole.
So you're talking about the Event Horizon Telescope, EHT.
Yes.
Yes. So what that is, it's a collection of radio telescopes that are spread around the world. Now, what they do is they do what's called interferometry. And so there's a little bit of the distance between the different telescopes and the black hole is a little bit. Not very much because the Earth is small and the distance to the black hole is so big, but a little bit of difference. And so what they do is they put all of those differences together, and they can get a very good image of a very small object. So they got that black hole in wherever it was, another galaxy, M83, I think it was. But what they also got was they did get an image of our black hole in Sagittarius. But they were having some problems with the data analysis. And so they have not yet released that image. But yes, you will see sometime a picture of the black hole in our galaxy.
So it is harder.
This is actually how the science works.
But it is harder to take a picture of our own black hole in our galaxy than another in the galaxy, because the picture of the black hole, the first one is coming from another galaxy in Cygnus 1. So it is possible, but it is not as easy as before, like that, Professor. Professor? Can you hear me, Professor? Yeah, it seems like Professor is leaving this room. Maybe we can give a time to Professor re-entry the Zoom meeting. Or maybe Professor is swallowed by a black hole. Okay, sambil menunggu Professor, while we wait for the Professor to be back to the room, we will have another question from, yeah, another one from Sindo Abdullah.
Okay, can anyone hear my voice? Apakah suara saya terdengar?
Oh yeah, Mas Sindo, maybe we have to wait for the professor to be back to the room.
Okay, okay.
We have another persons to raise their hands to get the questions. Please host to type the name of the participants who wants to give questions. So yeah, based on what Professor said, that it is, but yeah, it took time. It takes time because we do know that we are on the edge of our galaxy. We're not the center. We are not in the center. We are in the edge of our galaxy. So toward the center, we find a lot of obstacles. We can see that even with our eyes, when we see the night sky, when we see the Milky Way, we see a lot of dark area, and those dark area is actually a dust, stardust, and then black matter, something that not make us easy to see something in the center. So while the galaxy pictures of Cygnus 1, it is easier because we are seeing not in the disk of the center. We do know that Cygnus is in the galaxy, it's in the sphere of galaxy, but it's not at the center. We do know the center of galaxy is in towards Sagittarius and Scorpius. The Cygnus 1 is in the Cygnus constellations, not at the center. So it is easier to observe what's in Cygnus. It's easier than than when we see the Sagittarius, because Sagittarius is a lot of stars there, a lot of dust. So it is it's possible, but it took a lot of time to take a picture of our galaxy inside the Sagittarius constellation. So we do know Sagittarius A is, yes?
I think the professor is back.
Yeah, sorry, I had an internet failure.
Okay, welcome back, Professor. No problem.
Suddenly everything froze.
So you restart then.
I restarted.
Okay. So you have anything left to answer the questions about how to take a picture of our own black hole in our own galaxy?
I think I said the whole thing. They already have taken that picture in the radio, yep, but they have to work on the data analysis. So you will be seeing it soon.
So it is harder to take a picture of our own black hole in our galaxy because of it is toward the center.
I'm not sure what the reason is why they had the problem, because they're looking in the radio. We can't look at it in the visible because there's so much dust in the way.
Yeah,
But
so
they
much
were
dust.
looking at it in the radio, and that's much more transparent in the radio.
Ah, okay. Yeah. Okay, that's the answer from Professor. Thank you very much for the questions. Now, for Mr. Sindo Abdullah, please, you can give us the question.
Okay, thank you very much. Let me introduce myself first. My name is Shido Abdullah. I'm currently a physics student at Bandung Institute of Technology. It's an honor to ask you a question, Professor. And my question will be about your statement about it is important to do curiosity-driven research, but from high school, I think people always say that if you want to do a research, you need to have a reason that people around you can actually it should be useful for the communities. Something that just curiosity driven, I think, is not something that interests people in Indonesia, I guess. What do you think about it? Yeah, what do you think about it? It's is it what is more important at curiosity driven research or community driven research? Like you need to something that you need to the research need to be useful in some way. That's my question, Professor. Thank you very much.
Yeah. No, I know it's a difficult thing to say when people need help now. Why am I saying that you need to study black holes? How will that help? But I think that what you really need is you need a broad base of science. If you have this broad base of science, then you will have people who work on everything, who work on your application-related problems, on pure science. Now, the thing is that when you're working on problems that you see in the field, you get so caught up that it becomes a very narrow field, and you're solving the problems of today. In my opinion, when you do basic science, the things that you do and the things that your students do, because your students are now taught to think in a slightly broader sense, or in a much broader sense, they're taught to think about everything, that I think you start looking out of the box. You don't just work with the farmers on their crop techniques. Rather, you work on new ways of farming. So I feel that there is a place for, I feel that the work that you do in curiosity-driven science, I believe strongly that will feed out into everything else. I think that if we only do science, if we only work on better cars, better tractors, better pesticides, then we don't we don't change the paradigm. It's only when we think of these broader issues that we can hope to change the way the world is. I mean, we know now that the way we're going, it's not sustainable. You know, climate change. I mean, you know, every year I can see the difference in Bangalore from 20 years ago. It's much hotter now, and we see this. And this is what we do when we get so focused on these problems. I mean, it's why I give talks, actually. I give talks because I feel that it's important. I actually am quite passionate about the work that I do. I do enjoy it. I'm happy that someone is actually paying me for this. And I think it's important to convey that enthusiasm.
Yeah, so the paradigm is something that we first have to change, because that's the only way to make people know what's important of the science, what's important in astronomy, what's important of space astronomy, because without that paradigm, people will not know, and also people will not agree, people will not understand about what is the importance behind those ideas. That is very, very enlightenment comment about this questions. Thank you, Professor. So before we proceed to another questions, I have a question from our follower in Instagram asking about from Mila Izzatul Iksanti. What is your opinion, Professor, about the issues of the advancement of spacecraft, such as space debris, the Starlink satellites that interfere with astronomical observations, as well as radio waves for space exploration? So what are the efforts of astronomers to solve this problem? What do you think, Professor?
Yeah, no, this is a serious problem. And you know, I think 35 more Starlink satellites were launched yesterday.
Yes.
And as I said, I'm not really an amateur astronomer, but I do know that anytime you want to take a picture in the sky, there's a good chance that you'll get a satellite through it. And if we start moving towards these tens of thousands of satellites, I think that it needs to be thought of. I really do think that we should not allow rich people to just do whatever they want. We should. There has to be some discussion on this. You know, we don't allow mining in every area. We have environmental regulations, and the sky is something that we've looked at for thousands of years. We've had a sky, and now suddenly you want to put 20,000 new stars in the sky. I don't think that's right. And so how we handle it, I don't know. But I do think that there should be a discussion. Obviously, we need some number of satellites. We have communication, we have remote sensing, weather satellites. So we have some amount of satellites. But how we limit the number, that has to be discussion. You can't just launch 20,000 satellites. Tomorrow, Jeff Bezos will launch 100,000 satellites. And then we just can't do astronomy. And more than that, you know, amateur astronomers, you go out, you look at the sky. What sky will you look at? So I think it's very important.
Yeah.
But I don't have. I'm sorry.
Yeah. Ironically, one of the advantage of those Starlink satellite is to make internet is accessible for the rest of the world. So it's kind of ironic for this time.
But I don't believe it.
You don't
All
believe
our
it?
is now through fiber optic cable. So how can you match that?
That's right. That's right. We can use optics. We can use fiber optics for this. I agree with you. Okay. Thank you for your answer. For the next questions, we allowed to. Okay.
Given you want to ask, please.
For Gavin Ataya Sabian. Okay, Mr. Gavin, please.
Thank you. First of all, my name is Gavin Ataya Sabian. I am a student at 49 Senior High School, Jakarta. Professor, I want to ask you a question. Lately, we've been seeing a lot of companies like SpaceX and Blue Origin trying to commercialize spaceflight. What are the effects of that, and is it a good thing?
Yeah, I think in general, I do think it is a good thing. Now, you know, I grew up again, my academic career was when there were big spacecraft. So I showed you the few spacecraft. It's a huge Delta II rocket and a huge mission. Now, for lots of science, you do need big instruments. So for JWST, they have the James Webb Space Telescope. They have a 6-meter telescope. And so for a 6-meter telescope, you need lots of money. I think they're somewhere in the $5 billion range. And you need a big telescope. But there are also things that you can do with small telescopes and small instruments, which is what we do in my group. And what companies like SpaceX have done is that they brought the price of going into space they made it much cheaper. SpaceX and the CubeSat group, the CubeSat revolution also. So now you get lots of these CubeSats, which are small satellites. So we actually bought one. We haven't used it yet, but we bought a CubeSat for our group. And it makes it much easier to build space payloads. So this is what we're using it for. They've changed the way we think about space. We used to think about space as being very difficult. Difficult to do space. You had to be rich. You had to be at a rich university. Now we've changed it. We've changed that paradigm so that you can do things on a much smaller budget. And you can do it instead of buying all this space qualified equipment. You can actually do it with stuff that you go to the city market and buy. Of course, it might fail, but you haven't wasted that much money. So on the whole, I think it's been a good thing. It hasn't yet got down to the price limit, to the price level where I can say, you know, I'm just going to buy a launch. So so in my group, we built instruments, but the price of a launch is still about $100,000. And so that I can't afford. But you know, if it comes down to maybe $10,000, then maybe I can say, okay, I'll use my retirement savings to fund a small mission. So on the whole, I think it's been a good thing. The bad thing is this whole Starlink thing and all that, you know, good and bad.
So to launch rich people to go to outer space is a good thing, right? So it's a good use of rich people, not the other one.
And keep them there. Go to Mars.
Yeah.
Okay. Okay. Thank you very much for your answer, Professor. We hope that it's answer your questions.
The next, Trinadia, you can ask the Professor.
Okay. Trinadia, please. Trinadia.
Still connecting, maybe.
Okay, Trinadia, please.
Please, Trinadia, Mister.
Trinadia, are you there?
Mic-nya belum nyala. Di next aja dulu ke Tania.
Okay. So the next one is Titania. Titania, please. Please give your question.
Okay, hello, Professor Murthy. My name is Tania. I also used to study astronomy in my bachelor and master. And I have a follow-up question from the previous one about the rich people launching a lot of stuff to the space. Is that actually like a plan to make international regulation about this? Is there actually an effort from the International Astronomical Union to make a international regulation that, oh, we can't really launch a lot of things to the space because it's kind of crowded over there, for example? Or is there any effort from any other organization so far?
So the short answer is no, and let me explain that a little. The idea behind going into space was always a sort of self-regulation. So you would not do anything to hurt other people. And so that's worked more or less. And people didn't want too much regulation, because once you have regulation, then you know it becomes more expensive for everyone. So they sort of thought, okay, let's just make sure that everything works. So you have some things that work out. If you have 2 satellites, you have insurance, and basically the launching country is responsible for their satellite. So some regulation. Now what happened is that suddenly Elon Musk said, okay, we'll launch some, whatever number it was, 10,000 satellites. And this took everyone by surprise. No astronomer, there was no discussion anywhere. He must have got clearance from the FCC or whatever the American organization is, but really no discussion. And so now the International Astronomical Union, unfortunately, we're a science organization. And so for us, we have no regulatory power. So the people are trying to talk to everyone, trying to talk to Elon Musk, trying to talk to the space agencies. And so hopefully we will all come together and we will make some regulations. But I am actually not that hopeful because Musk himself, he said, someone pointed out that it's impossible to do astronomy. And he said, why don't you just go to the moon? And that's not really an answer. So, so we're working on it, but you know, it's not easy. There have been some successes from the International Astronomical Union. So for instance, there are dark sites in there. They worked with areas to try to darken the sky. You know, some simple things you can do instead of having street lights that shoot out light in all directions, you have them only come down. And you have areas which are reserved for astronomy. So we have the giant meter wave radio telescope in Pune. There, no cell phones are allowed. So you worked with them in some ways, but in general, it's difficult.
Yeah, it's difficult to make regulations if we talk about outer space, because when you have a lot of money, you can do a lot with your missions throughout outer space. But we hope that.
I'll tell you an interesting story. You know about the Israeli moon probe that landed, Beresheet. They wanted to go to the moon, and they almost made it to the moon, but then they crashed. It turns out that one of the payloads on that satellite was these water bears. You know, these small single-celled organisms that can live almost anywhere. And the people who launched these water bears, they didn't tell anyone. And so this is a problem, because now you go there and you're worried about, when we search for extraterrestrial life, we don't want to have contaminated it with Earth life.
Yeah.
And there were no regulations. They hadn't told anyone.
Yeah. Yeah, we do heard about those about those organisms that sends to outer space. It is very, very important to keep the outer spaces clear from what coming from the Earth itself, because when we want to know, when we want to make a research about SETI, it is important to have very original data from outer space.
Yes.
Okay, we still have 2 or 3 more questions. Maybe who's the next? Maybe Miss Nadia, if you can't access your camera, maybe you can just write down your questions.
Or Mr. Natane?
Okay, if not, maybe. Okay, for a while. Maybe I can give another chance for other people. Okay, while we wait, I have a question actually, Professor. You mentioned about why do we send a lot of satellites into the orbit and ruining our view of the night sky? Why don't you just put that on the moon, for example? Maybe you ever heard about the ILOA, International Lunar Observatory Association.
Yes, I was supposed to give a talk there in China and then in Thailand, but then of course the virus came, so.
Oh, great, yeah. We actually joined those seminars several times in Indonesia, and we heard about the idea of putting the telescope over the moon surface.
Yes.
So my question is, it is one thing to put the telescope into the orbit. It is very, very difficult task. And putting the telescope into the moon surface is another whole level. So it is really, really important to put a telescope on the moon, or we just focus to put it on the orbit? Or what do you think about this?
We actually studied this for our telescopes in the ultraviolet and visible, and we are actually better off in space, because you spend all that effort in going into space. We can do just as well from space. Where the moon is good is for radio astronomy. So what you can do is you can put a big telescope on the back side of the moon, and there you don't have to worry about all this radio transmission from the Earth. You can make it big, and that's great for this stuff like searching for black holes, because you have a huge telescope that's very stable and very quiet. For our own telescopes, probably we're better off in space, because we can get better stability, point wherever we want. And we don't have to go to the trouble of going to the moon.
But talking about your experiences in Goddard Space Flight Center, which one is more cheaper, to put the telescope in the orbit, or is it on the moon?
No, to put it in orbit. To put it in orbit is cheaper. Because to go to the moon, you have to go there, unless maybe there are people already on the moon and they can build it for you, then okay. But otherwise, it's cheaper to do it in space, because you don't have to spend that extra effort in going to the moon.
Including
we actually had a lunar payload. We were working with an Indian company, but part of the Google X Prize. And so that's what I was going to talk about at the ILOA. So we have an instrument that we were going to put a small telescope on the moon.
That's great.
It's built, it's sitting in our lab.
Oh yeah. Yeah, we heard about the Chandrayaan missions 1, 2, and 3. Yes. It is very successful missions from India to go to the moon. Yeah, we want to congratulate Indian for this, because in here we are we still have a long time and a long way to do the same thing with Indians too. Okay. For the next question is from Nadia. Are you there?
Are you there, Nadia? Maybe Mr. Aditya.
Okay, Mr. Aditya, please.
Okay, is it working?
Yes.
Yeah, we heard you.
Okay. Hello, Professor. So I'm Aditya. So actually, I'm also a member of HAAJ also. So yeah, I'm graduated from the ITB for physics. So okay, this might not be too related to the overall topic, but yeah. In our organization, we actively do kind of science communication to general public. But then sometimes, yeah, you know, like we got lots of like science deniers, like in nowadays, like people. I mean, like you can see everywhere where people just refuse to wear a mask or something like that, and like especially for the space-based kind of astronomy, like and progressive that is related to the astronomy, like. How can we kind of build to communicate this like in a way that we can like reach people to be more understanding, to be like what are we actually doing, and what have we progressed, and what is the benefit of like doing all of these exercises. So yeah, I think that's it.
No, I'm sure that that people like you are much more experienced at this than I am. What I do is whenever anyone asks me, I always accept. So that's what I do. As far as reaching outside, you know, I have a Facebook account. I don't use Twitter, but I use Facebook. I try to reach people that way. But I write a newspaper article every now and then, but doesn't have that impact that I think is needed. And how we do that, I really don't know. It used to be better because Indian TV stations, they used to actually be interested in science. Now they're interested in movie stars and this poor guy committed suicide a month ago, and so every news station, that's all they're interested in. But they used to be interested in science, and that had a lot of impact. Now I don't know, and I am honestly quite worried, because you get so much bad science out there, and how we communicate, how we tell people that no, the world is so interesting, you don't have to invent things. I don't know.
Yeah, it's become a common problem now. So you
yeah,
have,
it's a very challenging until now. Yeah.
Yeah.
Yeah, I think it's a very challenging times. Yeah, I think it's just a matter whether we should not give up, right?
Yeah.
Yeah.
On
Okay.
the
Thank
plus
you for
side,
Yep.
on the plus side, there is a lot of ways that people who are interested can learn. So many YouTube videos, so many, so much good information on social media. But if you don't want to learn, then there's also so many bad ways to go. I don't know what the answer is.
It is also happened in India, Professor. A lot of talks about science.
We have a lot of talks about science, but at the same time, we have all of this religious influences.
Okay.
You know, people going back and saying Ganesha was. I think you know all of our gods. So
Yeah.
Ganesha was an example that in those days they had. You know, plastic, whatever it was, they could put heads on people. So all of this has become increasingly bad.
Yeah.
That you get a lot of this. What people are especially doing is that they're going back 5,000 years ago, and they're saying we were so great then. We knew everything 5,000 years ago. That's not right. So it's difficult.
A common problem in developing country like us.
Yeah.
Okay. Thank you very much for Adisetya for your question, and we proceed to next question is for Mr. Nathel Pascal, please. Mr. Nathel, are you there?
Okay, I'm here. Okay, I'm here. So good afternoon, Professor. My name is Nathaniel Pascal. I'm 16 years old. I'm a student in Depok. And my question is probably more focused at historical background of discovery. So my question is how the black hole discovery was found. Is it was found from the theory that was proven right, or is it started from any space phenomenon?
Okay, so the black holes, we have known that they have existed for many years, many decades, because of theory. The evidence for the black holes, for the first evidence for black holes, came from these accretion disks. I think this is true. I think the first evidence came from accretion disks around stars. So we had these very bright objects which put out a lot of radiation and looked like they look very small. Places like Cygnus X1. So these I think were the first evidence for black holes. What really convinced everyone, or what really showed everyone that black holes existed, was the kind of stuff that I showed for M84, or the center of our galaxy, where they look at rotational velocities around the center of galaxies. And so they find that the stars are going so fast that there has to be a lot of mass, several million solar masses, in the center of that galaxy. And if you have several million solar masses in the center of our galaxy, that has to be a black hole. So there has always been this dynamical evidence for black holes. And I think I would consider that a direct evidence for a black hole. What many people would say is that the first direct evidence for a black hole came with LIGO, when they measured the gravitational waves from those two black holes that collided. And that you're really observing a black hole directly rather than observing the effects from the black hole. Other people might say that the first evidence for the first time you observed a black hole would be from the Event Horizon Telescope, where you saw the picture of, you saw the actual picture of the accretion disk around the black hole. So I would say that we've been confident that black holes have existed for at least 50 years, but really the evidence started coming in maybe about 20 to 30 years ago.
Thank you,
Now
Professor.
we know there's a black hole in the center of every galaxy.
Okay, thank you, Professor. We hope that can answer your question, Natal.
Yeah.
Okay. Yeah, it is very interesting, but sadly, maybe we only have a time to only one more questions. This is from Trinadia Kunyasari. She asked that the question is, are there spacecraft waste or debris in the space? What are the impacts? And maybe it's disrupting or dangerous or something else.
Yeah, no, this is a serious problem. There is a lot of spacecraft debris out there, and unfortunately, there have been some deliberate attempts to put in more debris. There was the Chinese test where they shot a rocket up and exploded a satellite. There was the Indian test of 2 years ago, I think, last year maybe, where again they exploded a satellite. And so there's so much debris out there that people are starting to get worried that you might have a chain reaction. I don't know if how many people have seen Gravity, the movie with Sandra Bullock and what's his name? Anyway, the movie Gravity. But what might happen is that there might be so much debris out there that it becomes impossible to launch any new satellite. So now what is, again, you know how hard, I told you how hard regulations are, but now when people launch satellites, they're supposed to have a deorbit. Every satellite has a life, and at the end of its life, it's supposed to come back down to the Earth in a controlled way. Now, there have been some bad examples in the past. There was a Russian mission which crashed in northern Canada. It was a nuclear-powered mission, so it left a trail of radioactive waste across northern Canada. You may remember the Skylab mission, which I think was about 5 years ago, and no one knew exactly where it would land. So people thought it might land in Australia. You know, if you have a satellite land on Sydney, then that's a problem. So there have been some uncontrolled landings, but now, in principle, every spacecraft that goes up is supposed to come back down in a controlled way.
Yeah,
but you don't know. You can always have this chain reaction.
Another ironic thing that the SpaceX owned by Elon Musk is developing and making a technology that rocket can be back again and it can be reused, and it's actually reducing the space debris for this case.
Right, right.
Yeah. So yeah, there's a lot of things that we do know from the science. We also know from the movie like Gravity, the dangers of the space debris, and we hope that is not become a very serious problem in the future for the space exploration. So, Professor, this is my own questions. Maybe become the last question for this session. In the first of your presentations, there is a quote from von Braun that said that the Earth is a cradle for us.
Yes.
And then we should go to outer space to reach the knowledge more. I talk about the space explorations also like the missions to go to Mars and everything that going away from the Earth. I want to ask your opinion. Is it true that the Earth is it true that humans, it's meant to be leaving the Earth? What do you think about it?
Yeah, you know, again, as a personal note, I grew up in the 60s and 70s, and I grew up reading science fiction, the golden age of science fiction. And so everyone said, we will be on Mars, we will be on Jupiter, we would have bases on Titan, maybe even Pluto. And so if you had told me back then that we still would be struggling to reach the moon, I wouldn't have believed it. So this was what I grew up with. But now I'm beginning to think it's so difficult for us to live anywhere else. I think it'll be great if we can go to Mars and explore, if we can go to Titan and explore. But I think it's better done with robots. I think we belong on the Earth. And I'm happy to have bases. I'm a fan of spaceflight. I'm excited by it. And I think it's great if we go to Mars and set up a base there. But for humanity as a race, I think we have to be on the Earth. I don't believe all this about setting up space stations. And I mean, I believe in setting up space stations, but I don't believe in setting up space cities. And the most I'll say is a space hotel. We'll go stay there for 5 days and then come back home, where we can walk outside.
Okay. Yeah, we belong to Earth.
What do you feel?
Okay, we belong to Earth. Thank you, Professor. So this is this is the big reasons, the big example for how we should protect the Earth, how to make the Earth is sustainable for our future. It is the only way that we can make the Earth is sustained for our future generations. So thank you very much, Professor, for your time and for your sharing of knowledge about this interesting topic about the space astronomy. But unfortunately, the time is up. And so we also thanks for you for the participants that become part of this project, Meet the Astronomer of IAU. So thank you again from Professor Jayant. Success for your life. Take care in this pandemic situation. So I will give to the master of ceremony to proceed. Thank you very much, Professor. Thank you very much for everyone. Take care and be safe.
Thank you all for coming.
Thank you for Professor Jayant, and thank you for Muhammad Rehan. Before we leaving the meeting, please let the camera on, and we will be take a screenshot from this meeting.
Okay, open the camera. Take a picture. Okay, we wait for the host to take the pictures of us. Please, camera. Ronald Marcel, where is your face?
Wait. One more.
Okay, one more.
Yeah.
Okay, done. Done.
Yeah. Thank you, Mr. Indra.
Okay, is it done?
Dah.
Okay.
So,
Thank you.
Okay, thank you, Professor. Thank you, everyone.
thank you, everyone.
Be safe.
Okay.
Thank you. Thank you.
Thank you.